Hello everyone, welcome to Xenon Circuits. This will be a crash course on basic electronics. The objective of this crash course is to aid the students preparing for campus placement drive in electronic based companies. The intended audience are pre-final and final year undergrad students specializing in electrical electronic engineering and pre-final and final year diploma students specializing in electrical electronic stream. The syllabus covered in this course include basic electrical circuits, analog and digital electronics. So the question that can arise in your mind is, what sets this course apart from the existing available courses? Rather than the conventional bottom-up approach, this will be covered in a top-down approach. You will unlearn and learn several concepts by solving problems and develop a better intuition while analyzing and designing circuits. So the approach which we are going to follow here is we will be giving a set of problems, and then while solving each and every problem on the way we are going to learn the concepts behind it. That will be helpful if you are if you want a crash course and if you are preparing for an immediate uh, campus placement drive. Without further delay, let's dive into the course. Okay, the first question is find the RAB, which is the R equivalent if all the resistors are of 1 ohm each in this network. So just by looking at this network, we can say that there are several resistors. Some of them are connected in series, some of them are connected in parallel. But this is something which is neither series nor parallel, right? Some of you might be able to recollect that this might be the Wheatstone bridge, which you might have learnt in your high school physics, right? Let's name the nodes first. So this node is called A, this node is called B, which means this is also B and this is also B, as these are shorted, right? Let's name this as C and let's name this as D. Let's name this as E. Okay. So across D and B and E and B, the network is same. Whenever we have an R equivalent circuit, we should try to solve it in the opposite direction. Let's say if we are going to, if we are given a network where this is the open, then we need to solve it by coming at the opposite direction. Okay. Let's take the network between the nodes D and B. So D and B is nothing but a Wheatstone bridge, right? So D is here and B is here. This is 1 ohm, 1 ohm, 1 ohm and 1 ohm. If you remember the Wheatstone bridge concept, which states that the bridge is balanced if the ratio of this impedance and this impedance or resistance is same, right? So this is 1 and 1 and this is 1 and 1. So this is a balanced bridge. In a balanced bridge, the current through the middle arm would be 0. So the current through this resistor is 0, which means that becomes an open circuit, right? So if I draw the simplified circuit of that network, it becomes 1 ohm, 1 ohm, 1 ohm, 1 ohm across D and B. 1, 1, 1, 1. Now, just by looking at it, you can say that these two are in series and these two are in series. So this becomes 2 ohms, this becomes 2 ohms, and 2 ohms and 2 ohms across D and B are in parallel, right? So this becomes 1 ohms, right? Because these two are connected in parallel, and we know that in a parallel R equivalent is R1 R2 by R1 plus R2, correct? So over here it becomes 2 into 2 by 2 plus 2, so it becomes 1 ohm. Similarly, for two resistors connected in series, the R equivalent is R1 plus R2, right? Now, D and B, we solved the R equivalent for D and B, the network between D and B. And if you take a look at the network between E and B, they are same as in D and B, correct? So the R equivalent across E and B should also be 1 ohm, right? So if I further simplify this circuit, the A and B, between A and B, this becomes 1 ohm and then 1 ohm, 1 ohm, 1 ohm, then over here 1 ohm, and over here it becomes 1 ohm, and this is A and this is B, correct? So once again, we have a Wheatstone bridge over here. So this is the node C, these are the nodes D, and these are the nodes E and B, correct? So once again, if we try to solve this network, we'll be getting still the 1 ohms. So A and B further becomes 1 ohm and 1 ohm. So RAB is nothing but 2 ohms. Okay. So if you are someone who forgot how to calculate the R equivalent for series and parallel resistors, or if you are wondering how we got this formula, let's get into the explanation. Also, in case if you are getting selected to the written test in your interviews, the interviewer might ask you to derive the R equivalent for series and parallel resistors. Okay, let's check it out. So assume you have a battery that provides a supply voltage of V and current I, and then we have two resistors R1 and R2 connected in series, right? On what basis I am saying this is series? The electrons that are entering from, I mean, electrons ideally would be coming from the negative terminal of the battery or the cathode and then enters the positive terminal, right? Whereas the current will be leaving from the positive terminal and will be entering the negative terminal. And we know that current flow is nothing but the flow of positive charges or absence of electrons. This is the electron flow, right? Okay. And as you can see here, the electron that is flowing over here has no path to divide. So the electron that enters R2 will be entering R1 and enters the battery. So all these three elements, the battery, R1, R2, are connected in series, right? So the current across them should be the same. And everyone would be aware of Ohm's law, right? As you would have learned in your high school physics, Ohm's law states at constant temperature, the potential difference across two terminals is directly proportional to the current flowing through them, right? And the proportionality constant is R, which is nothing but resistance, right? Okay, so you might also be aware of Kirchhoff's voltage law and Kirchhoff's current law. Kirchhoff's voltage law states that in a closed loop, the sum of voltage rise is equal to the sum of voltage drop, right? So if we apply KVL to this network, this becomes the voltage rise is equal to V, and the voltage drop equals to IR1 plus IR2, right? And I is common, you can take this becomes R1 plus R2, and V by I is nothing but the R equivalent, and that is equal to R1 plus R2. Okay, this is how we derived this formula. Similarly, if two resistors are connected in parallel, if two elements are connected in parallel, then both the terminals should be connected to each other. Only then we call it as parallel. So you can see that the terminal A and the terminal B of both R1 and R2 are connected across each other, and also to this battery with supply voltage of V and current I, right? So all these three elements, the voltage, resistors R1, R2 are connected in parallel. When we know that the voltage across this battery is V, and if elements are connected in parallel, then the voltage drop across all the three voltage across all the three elements or all the parallel elements will be the same. So it would be V over here as well as over here. Okay, the main reason behind this is you can see here the resistance of an ideal wire is 0, and if a current flows through that, the IR will still be 0, right? IR is nothing but the voltage drop, which means the voltage drop across this path and this path are 0. So the whatever voltage we are seeing over here across the battery will be reflecting across R1 and R2. So if we apply Kirchhoff's current law, what happens is the current that enters A gets divided across R1 and R2. It divides as I1 and I2. Okay. And what does Kirchhoff's current law states? The sum of current entering a node is equal to the sum of current leaving, right? So here the current that's entering is I, and the current that's leaving is I1 and I2. And by Ohm's law, we know that I equal to V by R, and I1 is nothing but the current through resistor R1, and the voltage across resistor R1 is V, and voltage across resistor R2 is V. So this becomes V by R is nothing but this becomes, I mean, V is common, so this becomes 1 by R equivalent equal to 1 by R1 plus 1 by R2, right? And if we take the reciprocal and bring R equivalent to the numerator, R equivalent will become R1 R2 by R1 plus R2. Okay, this is how we derived the R equivalent for series and parallel resistor combination. So in this lecture, just by solving one R equivalent problem, we got to know the R equivalent in series parallel network, how the formula came into existence, and then how current behaves in series elements, and how voltage behaves across parallel elements, right? We will further discuss the current division and voltage division in the next lecture. Thank you.